The James Webb Space Telescope is upsetting the apple cart. All of a sudden, we realize that we may have to rewrite all the textbooks about the beginning of the universe.
Our view of the universe has been changed forever by James Webb. Just 3 years after its launch, the premier telescope has sent back hundreds of thousands of dazzling photos, revealing the vast universe like never before. And now, NASA's $10 gamble is heading us to a new space adventure like never before. It's an adventure into a strange world located in the Kuiper Belt, a zone beyond the orbit of Neptune brimming with hundreds of thousands of rocky, icy bodies, each larger than 100 kilometers across, as well as 1 trillion or more comets. Well, can you guess it? Yep, it's Pluto, a largely unexplored territory. But now, things are about to change with James Webb. Its great power allows us to see this dwarf planet in unprecedented detail, revealing secrets and mysteries beyond our wildest imagination. Join us as we dig deep into the most stunning revelations about Pluto. Pluto, once considered a cold, distant world, has been transformed in our understanding. No longer is it just a small, frozen chunk of rock drifting at the edges of the solar system. Instead, this mysterious dwarf planet now appears to harbor a dynamic and complex interior, possibly with an ocean lurking beneath its icy crust. The idea of a liquid ocean residing beneath Pluto's surface has gained considerable support in recent years, largely due to new observations and data. The theory is supported by several intriguing features visible on the planet's surface, such as its system of extension fractures and the absence of large, well-preserved craters in certain regions, which suggests that Pluto is far more geologically active than previously thought. These findings point to the possibility of ongoing internal processes beneath Pluto's frozen exterior, which may indicate a subsurface liquid ocean. This hypothesis about Pluto's hidden ocean isn't new. The idea has been around for some time. In fact, scientific discussions and publications from as far back as 2006 entertained the possibility that celestial bodies beyond the gas giants might harbor subsurface oceans. Among these was Pluto, a dwarf planet at the outer reaches of the solar system. In the years that followed, researchers began to build on these ideas, especially as technology advanced and new space missions explored distant bodies. While these early theories were speculative, the New Horizons mission, launched by NASA, provided the data that would give these hypotheses newfound weight. The spacecraft's flyby of Pluto in 2015 provided the most detailed images and data ever collected about the dwarf planet, shedding light on its surface and revealing a landscape far more complex than anyone had imagined. The New Horizons mission represented a major milestone in our exploration of Pluto. Prior to this mission, our understanding of the distant world was limited to blurry, low-resolution images taken by the Hubble Space Telescope. But when New Horizons arrived at Pluto, it presented scientists with their first close-up, high-resolution images of one of the most mysterious objects in the solar system. The spacecraft's camera systems captured breathtaking images of Pluto's surface, revealing soaring mountains made of ice, vast plains, glaciers, and even towering ice volcanoes. Perhaps the most striking feature, however, was a large heart-shaped basin on Pluto's surface, known as Sputnik Planitia. This basin, which is a vast expanse of nitrogen ice, also provided scientists with clues about the planet's geological history and its internal structure. The images showed a surface that was not only diverse and intriguing, but also indicative of dynamic geological processes at play. In addition to these remarkable surface features, New Horizons also revealed that Pluto has a remarkably spherical shape, a characteristic that caught the attention of scientists. This near-perfect sphericity, combined with the network of fissures and cracks visible on Pluto's surface, raised further questions. The spherical shape, in particular, is unusual for a body of Pluto's size, suggesting that internal forces may be at work. This could indicate the presence of a subsurface ocean, providing the necessary pressure to help maintain Pluto's spherical form. For scientists, these observations became tantalizing clues that something more complex and active might be occurring beneath the dwarf planet's icy exterior. Among the first to explore these ideas was Francis Nimmo, a planetary scientist from the University of California, Santa Cruz. Nimmo and his team noticed a significant feature on Pluto's surface that further supported the hypothesis of a subsurface ocean: the alignment of Sputnik Planitia with Pluto's largest moon, Charon. The icy basin sits almost exactly opposite Charon, an alignment that scientists have noted is highly unlikely to have happened by chance. The probability of this being a random occurrence is less than 5%. Instead, models of planetary formation and evolution suggest that when Sputnik Planitia formed, it may have caused the planet's surface to shift due to the internal redistribution of mass. The formation of the basin could have triggered the rise of a liquid ocean beneath Pluto's crust, which subsequently caused the planet's crust to adjust to the weight of the water and ice. This redistribution of mass may have also played a role in Pluto's present-day alignment with Charon. The existence of a subsurface ocean was further supported by the discovery of chaotic terrain on the opposite side of Pluto from Sputnik Planitia. This terrain is marked by a confusing jumble of ridges, cracks, and plains that are characteristic of regions on other planets and moons that have been subjected to significant seismic activity. Similar chaotic terrains have been observed on other celestial bodies, such as Mars, Mercury, and Europa, one of Jupiter's moons, and scientists believe they may be the result of seismic waves generated by asteroid or comet impacts. When such impacts occur, the resulting shock waves travel through the planet's interior, and when they reach the opposite side of the impact site, they can tear up the surface in ways that resemble the chaotic terrain found on Pluto's far side. To investigate this possibility further, Adine Denton, a graduate student at Purdue University, conducted simulations to model the effects of an asteroid impact on Pluto's surface. The simulations showed that a large impact could indeed generate the kind of chaotic terrain seen on Pluto. However, there was a critical caveat. For such an impact to have produced the observed terrain, Pluto would need to have a subsurface ocean of liquid water at least 150 kilometers thick. The presence of this ocean would explain the way the seismic waves from an impact could have affected Pluto's surface, as the liquid ocean would have helped to distribute the shock waves more evenly across the planet's interior. This study provided strong evidence for the existence of a subsurface ocean on Pluto, although some scientists, including Oliver White from the SETI Institute, have pointed out that the resolution of the images is too low to definitively confirm these findings. Nonetheless, the evidence for a subsurface ocean continues to grow, and it may ultimately require another mission to Pluto to settle the debate once and for all. If Pluto does indeed harbor an ocean beneath its icy surface, it raises fascinating questions about the planet's geological history and the potential for life. Most scientists had long assumed that Pluto's ocean would have formed under extremely cold conditions, freezing soon after the planet's formation. The initial theory proposed that the ocean would have started as a solid layer of ice and then later melted due to heat generated by the decay of radioactive elements in Pluto's rocky core. This melting could have led to the formation of wrinkles on the surface, similar to the way that an apple shrinks and wrinkles when it is left in the refrigerator. As the ice refroze, it would have expanded, causing the surface to crack and further deform. However, the observations made by New Horizons appear to contradict this theory. Instead of seeing signs of older wrinkles and newer cracks, the spacecraft's images show only cracks on the surface, suggesting that Pluto's ocean may have started as a liquid and has only partially frozen over time. One of the most striking pieces of evidence for this comes from images of a massive crack stretching across Pluto's surface. The crack, which extends from the planet's North Pole down to the South Pole and wraps around the entire planet, is reminiscent of the East African Rift system on Earth, where tectonic plates are slowly pulling apart. However, unlike the rift on Earth, Pluto's crack is not the result of shifting tectonic plates. Instead, scientists believe that the crack is a scar left by the freezing and expanding liquid ocean beneath the surface. This suggests that Pluto's ocean may have begun as liquid water and froze over time, with the process of freezing causing the planet's surface to crack and shift. The age of the crack further supports this hypothesis, as it indicates that the ocean began to freeze soon after the planet's formation. The potential for life on Pluto, while still speculative, has also captured the attention of scientists. In particular, observations of water that seems to have emerged from Pluto's ocean have revealed that it is red, suggesting that it may contain organic molecules. While this may seem improbable given Pluto's extreme distance from the Sun and harsh conditions, laboratory experiments have shown that radiation from solar wind and cosmic rays can produce complex organic compounds. If ammonia is present in Pluto's environment, these organic molecules could form the building blocks necessary for life, such as the bases found in RNA and DNA. In a groundbreaking study, Dale Cruikshank, a planetary scientist at NASA, and his colleagues revealed that Pluto's near side is rich in ammonia and organic molecules, providing further evidence that the dwarf planet could harbor the chemical ingredients necessary for life. Moreover, images of Pluto's far side reveal a red band of material, likely composed of organic compounds, that stretches across the planet's equator. This area, with its moderate sunlight and more temperate climate, is thought to be the most likely place where organic chemistry could occur. The discovery of liquid water, organic molecules, and potential energy sources such as sunlight provides a compelling case for the possibility of life on Pluto, if not life in the traditional sense, then perhaps the conditions necessary for life to emerge. While many scientists have been cautious about making definitive claims regarding life on Pluto, the recent discoveries have opened up new possibilities for the future. The fact that Pluto may harbor liquid water, organic molecules, and a source of energy is a significant step forward in our search for life beyond Earth. These findings represent a major breakthrough in our understanding of the potential for life in the outer reaches of the solar system. In contrast, some people, particularly UFO enthusiasts, believe that Pluto may harbor more than just simple organic molecules or a hidden ocean. They claim that certain images captured by the New Horizons mission show evidence of artificial structures on the dwarf planet. For instance, one image appears to show a mysterious smoky trail stretching across Pluto's surface. While NASA scientists explain this as a natural phenomenon, possibly sunlight reflecting off a methane cloud, some conspiracy theorists argue that it could be the result of smoke rising from an artificial structure. This claim has sparked interest among UFO enthusiasts, who see the discovery as evidence of extraterrestrial life or technology on Pluto. But if so, how does it affect us? Sure, the discovery of life on Pluto would fundamentally challenge and expand our understanding of what makes a planet or moon habitable. For centuries, scientists have been guided by a relatively narrow definition of habitability, one that assumes life requires certain environmental conditions: liquid water, a stable climate, and an atmosphere capable of sustaining life. These criteria are based on what we know from Earth, the only planet we know to support life. We tend to think of the habitable zone as an area around a star where temperatures are warm enough for liquid water to exist, but not so hot that it would evaporate, or so cold that it would freeze. Our search for life beyond Earth has largely focused on finding planets or moons that fit these parameters, whether in our own solar system or in the wider universe. However, the discovery of life on Pluto would force us to reconsider these assumptions and dramatically broaden our definition of what constitutes a habitable environment. Pluto, located on the outer edge of the solar system, is a world of extremes. It is incredibly cold, with surface temperatures averaging around -225 degrees Celsius. The atmosphere is thin, primarily composed of nitrogen, with trace amounts of methane and carbon monoxide. Pluto is bathed in weak sunlight, receiving only a fraction of the energy that Earth does from the sun. It is, by all accounts, a hostile and inhospitable place. And yet, if life were discovered there, it would force us to rethink what makes a place habitable and challenge our Earth-centric view of life. It would suggest that life could thrive in environments that are cold, dark, and otherwise hostile to the forms of life we know. One of the key implications of such a discovery would be the need to expand our definition of the habitable zone. Instead of viewing habitability solely in terms of temperature, liquid water, and a breathable atmosphere, we would have to account for the possibility that life could exist in regions of space that are incredibly cold and devoid of sunlight. This would open up a whole new class of environments that might be capable of supporting life, such as the icy moons of Jupiter and Saturn, or even distant exoplanets orbiting far from their stars. It would force us to rethink the fundamental conditions that life requires and might lead us to consider new ways that life could survive and thrive in seemingly inhospitable places. Life on Pluto would also challenge our understanding of what types of energy sources life can rely on. On Earth, most life forms depend on sunlight as the primary source of energy. Plants use sunlight to photosynthesize, and animals rely on plants or other animals for food, forming an intricate web of life powered by solar energy. But in the absence of sunlight, life on Earth has found other ways to survive. For example, deep-sea hydrothermal vents host ecosystems that do not rely on sunlight at all. Instead, bacteria and other organisms in these environments use chemical energy from the Earth's interior, specifically from sulfur compounds and methane, to sustain themselves. This kind of life is called chemosynthesis, and it suggests that life can thrive on energy sources other than sunlight. If life on Pluto exists, it is possible that it could rely on similar chemical energy, or even energy from radioactive decay in the planet's interior. Radioactive isotopes decay over long periods of time, releasing heat, and this heat could potentially provide a source of energy for life on Pluto. Such life might be living in deep subsurface oceans, kept warm by geothermal energy, or in other pockets where chemical reactions could sustain microbial life. In fact, life might not only survive in these extreme environments, but could thrive there, adapting to the cold, the darkness, and the lack of sunlight. Life on Pluto might look radically different from what we are used to, and it might use biochemical pathways that we are only beginning to understand. The discovery of life on Pluto would also remind us of the incredible adaptability of life. Earth is home to a staggering diversity of life forms, from bacteria that live in the acidic, boiling waters of hot springs to creatures that survive in the deep, lightless trenches of the ocean. This diversity demonstrates that life is extraordinarily resilient, able to survive in environments that we once thought would be too extreme to support any form of life. The discovery of life on Pluto would extend this understanding to a whole new realm of possibilities, suggesting that life could exist in environments we have long considered inhospitable. The implications of finding life on Pluto also would extend beyond the scientific community and into the realm of philosophy and ethics. Such a discovery would not only be a scientific breakthrough, but also a profound moment in human history, one that would challenge our understanding of life, existence, and our place in the universe. It would force us to question the uniqueness of life on Earth and consider the possibility that life is far more common than we ever imagined. If life can exist on Pluto, in the most remote and inhospitable corner of our solar system, what does that mean for the rest of the galaxy? Could there be other forms of life in the vastness of space, possibly even in places we have yet to consider? And if life can exist in such extreme conditions, what does it tell us about the potential for life elsewhere in the universe? From an ethical standpoint, the discovery of life on Pluto would raise profound questions about our responsibilities as stewards of the cosmos. If we find microbial life on Pluto, should we protect it from contamination or exploitation, even if it exists in the most remote and inhospitable environment imaginable? Would we have an ethical obligation to ensure that human exploration of Pluto does not interfere with the existence of life there, whether it be microbial or more complex? The potential discovery of life on Pluto would force policymakers, ethicists, and scientists to engage in complex debates about the morality of exploration, resource extraction, and the preservation of alien ecosystems. Should we interfere with Pluto's pristine environment for the sake of scientific discovery or potential commercial gain? Or should we adopt a more cautious approach that prioritizes the preservation of life, wherever it may be found? These philosophical and ethical considerations would be further complicated by the broader question of what constitutes life in the first place. If we discover life on Pluto, would we recognize it as life in the same way we recognize Earth's life forms, or would we need to rethink the very definition of life? Life on Earth is carbon-based, and our understanding of biology is based on carbon chemistry. But life on Pluto, if it exists, could be based on a completely different biochemistry, one that we have yet to discover or fully understand. This raises the possibility that our definitions of life may be too narrow, and that life might take forms and use processes that we can scarcely imagine. While the discovery of life on Pluto would undoubtedly be a monumental scientific breakthrough, it would also mark the beginning of a new chapter in the search for extraterrestrial life. Such a discovery would not signal the end of the search, but rather open up new avenues for exploration. If life can exist on Pluto, then it stands to reason that other icy moons in the outer solar system, such as Europa, Jupiter's moon, Enceladus, Saturn's moon, or Triton, Neptune's moon, could also harbor life, potentially under similar extreme conditions. The discovery of life on Pluto would likely spark a renewed interest in these worlds, leading to new missions and research aimed at understanding the potential for life on other moons and planets. At the same time, the discovery of life on Pluto could have implications for the search for life beyond our solar system. If life can exist in the frigid outer reaches of the solar system, we might begin to consider the possibility that life could exist on exoplanets that are far from their parent stars, or even on rogue planets that do not orbit any star at all. These planets, known as rogue exoplanets, float freely in space and could have conditions similar to Pluto's: frigid temperatures, thick atmospheres, and potentially liquid water in underground oceans. The search for life in these distant and cold environments would require a significant shift in our thinking and technological approaches. Instead of focusing only on the search for Earth-like planets in the habitable zones of stars, scientists may need to develop new methods for detecting signs of life in environments where light and warmth from a star are not available. The detection of life on such remote and inhospitable worlds would force us to rethink the definition of a habitable zone entirely. As technology continues to advance, so too will our ability to detect biosignatures, chemical signs of life, on distant exoplanets and moons. Robotic spacecraft, telescopes, and other instruments are already being developed to search for such signs, and in the coming decades, we may possess the tools to detect life in ways that were once thought impossible. Advanced spectrometers could allow us to study the atmospheres of exoplanets in unprecedented detail, searching for chemical compounds that could be linked to biological processes. Instruments like the James Webb Space Telescope and future missions could allow us to analyze the atmospheres of distant exoplanets for signs of life-related gases, such as oxygen, methane, or carbon dioxide, in quantities that would be difficult to explain without the presence of living organisms. These instruments could also be used to examine moons in our own solar system, looking for signs of life or conditions that might support life, even in places like Europa, Enceladus, or Pluto itself. Ultimately, the search for life is one of humanity's most profound and exciting scientific endeavors, driven by our desire to understand not only our place in the universe, but also the fundamental nature of life itself. The discovery of life on Pluto, whether it is microbial or in some other form, would be a reminder that life is not necessarily limited to the conditions we are familiar with on Earth. Life might exist in places we have not yet considered, and it might take forms that challenge our current scientific and philosophical frameworks. It would underscore the resilience of life, showing that it can thrive in environments once thought to be inhospitable, and it would raise profound questions about the nature of life in the universe. But while the discovery of extraterrestrial life is often viewed with excitement, there are significant and often overlooked dangers associated with such a discovery. One of the most immediate and profound risks of discovering signs of extraterrestrial life is the psychological impact on humanity. For centuries, humanity has operated under the assumption that Earth is unique, that humans occupy a special place in the cosmos. This anthropocentric worldview has been deeply woven into the fabric of human culture, religion, and philosophy. The discovery of extraterrestrial life would challenge these deeply ingrained beliefs, potentially leading to widespread societal upheaval. The shock of realizing that we are not alone in the universe could undermine people's sense of purpose and identity. For some, it might challenge religious beliefs, particularly those that hold humanity as a special creation of God. The existence of alien life could lead to existential questions about the meaning of life, our role in the cosmos, and the nature of intelligence. For others, the discovery might lead to a sense of profound isolation, questioning whether human beings are truly important or merely one species among many in an indifferent universe. Additionally, the discovery could lead to social unrest. In a world already grappling with political, economic, and environmental instability, the revelation that life exists elsewhere in the universe could exacerbate fears and anxieties. Some might see extraterrestrial life as a threat, fearing the possibility of invasion or contamination. Others might worry about the moral and ethical implications of interacting with alien species. In extreme cases, societal collapse or widespread panic could result from the shock of such a discovery. Another major danger associated with finding signs of life in the universe is the potential for biological contamination. The introduction of alien microorganisms into Earth's ecosystem could have catastrophic consequences. We already know that Earth's ecosystems are fragile and finely balanced, with even small changes in environmental conditions potentially leading to the collapse of entire species or ecosystems. The introduction of alien organisms, particularly those with vastly different biologies, could trigger unforeseen and potentially disastrous consequences. One of the most well-known examples of the dangers of biological contamination comes from the planetary protection protocols developed by space agencies like NASA. These protocols are designed to prevent the accidental contamination of both other planets and Earth during space exploration. For instance, when NASA sent the Viking missions to Mars in the 1970s, they took great care to sterilize the spacecraft to avoid contaminating Mars with Earth bacteria. Similarly, the return of samples from Mars or other planets would be carefully controlled to prevent the spread of alien microorganisms to Earth. But the dangers of biological contamination go beyond just protecting Earth from alien life. The discovery of alien life could also lead to the reverse scenario: Earth-based organisms contaminating other planets. If we are not careful, our own microbes could wreak havoc on potential alien ecosystems, disrupting their delicate balance in the same way that human activities have caused environmental destruction on Earth. There are also ethical considerations to take into account. The potential for biological contamination raises the question of whether we have a moral obligation to protect alien ecosystems from our own presence. If we were to discover life on another planet, should we simply leave it untouched, allowing it to evolve naturally, or should we attempt to study and interact with it, risking irreversible damage to its native biosphere? The discovery of extraterrestrial life also raises the possibility of encountering alien civilizations. While this prospect is often portrayed in science fiction as a potential for peaceful exchange and mutual discovery, there are serious risks associated with the potential for hostile encounters. The history of human exploration is filled with examples of seemingly peaceful encounters that quickly turned violent, such as the European colonization of the Americas. There is no reason to assume that alien civilizations, if they exist, would be inherently benevolent or peaceful. The Great Filter Hypothesis, a popular theory in the search for extraterrestrial intelligence, suggests that advanced civilizations are exceedingly rare because many intelligent species may self-destruct before reaching a level of technological advancement that would allow them to explore or communicate across interstellar distances. If this hypothesis is correct, it suggests that civilizations capable of interstellar communication or travel are rare, but also potentially dangerous. The technological gap between Earth and any alien civilization we might encounter could be vast, with unknown consequences. For instance, if an alien civilization is capable of detecting our signals, they might interpret them as an invitation to make contact. But they could also see us as a threat to their own survival, or as a resource to be exploited. The technological disparity between us and an alien species could lead to dangerous situations. Even a technologically superior alien species might not necessarily have peaceful intentions. It is also possible that an advanced civilization, if they were aware of our existence, might choose to quarantine or destroy us in order to preserve their own safety, much as humans have been known to quarantine or eliminate invasive species. Furthermore, the potential for military applications of alien technology or knowledge could exacerbate geopolitical tensions on Earth. The discovery of extraterrestrial life could spark a new space race, as nations scramble to gain control over any technology or resources that might be derived from alien civilizations. The militarization of space could lead to an arms race or even conflict between Earth-based powers, further destabilizing an already volatile global political landscape. In short, the search for signs of life beyond Earth is undoubtedly one of the most exciting and transformative endeavors of modern science. However, it is crucial that we approach this pursuit with caution, awareness, and preparedness. Only then can we navigate the profound and potentially dangerous implications of finding life beyond Earth. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.